Welcome back, Physics 180. We're talking about calorimetry in our Chapter 1, heat and temperature. It really comes down to this. We're going to use that Q equals mc delta T for substances, and we're going to look at mixing substances together. Most of the time, one of these substances is water, since it has a very well-known specific heat that's pretty high. So what that means is that it can change its temperature very little for pretty large inputs or outputs of energy, heat energy, right? Um, and it's commonly available and mixes with some stuff pretty well. So that's why we use that. The conservation of energy is really the key thing to this. Is that we're saying that Q is a constant. We kind of split up Q into, in this instance, hot and cold. Or I could just say if I had three things, Q1 plus Q2 plus Q3 equals 0. Now, of course, if you look close at this, you recognize that the Q hot, Q cold are the three things. One of these things, at least, has to be negative. But that just means that one of the things started out hot, and it had a delta T, a temperature change, that was negative, right? So the hot thing has a negative temperature change. The cold thing or things have a positive temperature change, but the heat is just flowing internally in a system. And the trick with calorimetry when you try to perform this experiment is isolating the things that are exchanging energy so they don't exchange energy with the room. So you don't have to keep track of the environment so much. So you can get a calorimeter, which is this insulated container for your calorimetry interactions to happen in, right? So if the temperature is increasing, Q and delta T are positive, energy is going into whatever that thing is. The system is one of these things, either the hot thing or probably the cold thing, or one of the three things, or two of the three things, right? Temperature is decreasing, that Q and delta T are of course negative, energy is transferring out of that thing. So the hot thing has energy transfer out of it into the cold thing or things, right? Let's look at an example. I'm not going to do tons of the math here, but I'll leave that for you. We'll get you a start and I'll show you what the answer is, and I'll leave you to fill in the middle. So we've got some metal, 0.05 kilograms. So that's what, 50 grams, right? It's heated up to 200 degrees Celsius in a furnace. And it's still solid metal. It might be glowing red hot or something, but it's still solid. It's not melted. I take that hot metal with some tongs or something, obviously, drop it into a beaker of water. They're 0.4 kilograms, 400 grams of water initially. And that water is initially at 20 degrees Celsius, sort of a cool room. Not really cold, but slightly cool, right? The equilibrium temperature after all the mixing is done is measured at 22.4 Celsius. I would like to know what's the specific heat of that metal. And then maybe I can compare it to some known specific heat values and figure out what it is. Well, let's use sub M for metal and sub W for water. What I'm going to say here is that Q metal plus Q water has to be equal to 0. And then I'm going to use that MC delta T, mass of the metal, C of the metal, delta T for the metal, mass of the water, specific heat C of the water, delta T for the water equals 0, right? Now remember, the final temperature of both things is the same. Their initial temperatures are, of course, very different, and their masses are different. So let's call this mass metal, and that 0.4 kilograms mass of water, right? With those, let me make a note of that. Mass water. This is temperature metal initial. This is temperature water initial. And this is temperature final, right? With that setup, and then of course I know the specific heat of water, 4,186 joules per kilogram degrees Celsius or Kelvin. If I want to be really, really careful with temperatures, I should always convert them to Kelvin. if we're just talking about temperature changes, which we are here, we know the final and initial temperatures of everything. So all we're talking about is temperature changes. Those are the same in degrees Celsius as they are in Kelvin, so I can just look at the changes. But let's, I'm going to skip the intermediate substitution and algebra of that Q equals mc delta T, and then solve for the specific heat of the metal. I called it sub X here, I guess. So yeah, let's change my m sub X, the unknown, right? Temperature sub X initial. And you can see it turns out to be 453 joules per kilogram degree C. That's in the range of a lot of metals. I'll leave for you to fill in the algebra that goes between the thing I wrote down in red and that final expression. If you have questions about it, hit me up. I can show you some details. But that's sort of the simplest sort of calorimetry example. Imagine mixing more than just two things, having some water and putting two different kinds of metal. Or maybe I say, well, the water's got to be inside of something, right? Maybe I've got a little, my calorimeter is made up of something that's exchanging energy with it, right? So maybe plastic or aluminum or something, a steel cup or something. Maybe I have more than one kind of thing that I need to keep track of that might change its temperature, right? So we'll probably do some calorimetry in the lab. There's a good hands-on lab for calorimetry. You could do simulations of calorimetries in GlowScript. That would be a pretty cool thing. Think about doing that. I may write one for you guys to work on. But these kind of calculations you should know how to do. Do some calorimetry problems from the homework, both the ones I've made up and the textbook problems. And I'm sure there are some good examples in the text as well to look at. Another complication that arises in this adding energy to and taking energy out of objects or systems is that materials can change phase, right? They change from one phase of matter to another, the phases being solid, liquid, and gas in this instance. We are not going to extend this to a fourth phase of matter known as plasmas. Plasmas have a whole host of complications that we're not prepared to talk about at this juncture. Mostly electromagnetism, because we separate charges and the charges start moving around and things go really crazy. But you can think of it this way. Remember that temperature is an average kinetic energy, so things are kind of shaking around. You add heat energy and things shake around more and the temperature goes up, right? Let's look at H2O. We'll start with ice, the solid form of it. I add some energy, things shake around more. I keep adding energy, things shake around more. Eventually, the ice melts and turns into liquid water. But it doesn't just happen all at once for free. It takes energy. I have to keep shaking until I shake them apart. And the bonds between the crystalline bonds break, and they're more weakly bound in a liquid, right? And then I keep shaking. Eventually, I shake them so hard they start flying apart from each other, right? Get even further away, and I get a gas. And that happens with most things, right? Most things have liquid, solid, liquid, and gas phases. There are some notable exceptions. Helium, I don't think there's even a predicted solid phase of helium. Interestingly, hydrogen, there are predictions of solid hydrogen. No one has ever confirmed the existence of solid hydrogen to date, although some people claim to have been very close, and it's of interest because it might be a superconductor. If you're looking for a cool field of study as a physicist or a material scientist, the search for metallic solid hydrogen is a really interesting one. Probably only happens at super duper high pressures. Anyway, let's look at this graph. Temperature versus energy change, kind of energy change per mass. I'm adding an amount of energy per mass to this stuff. So initially I start with some ice at minus 20 degrees Celsius. I keep adding energy. It's solid, it's a solid, it's a solid. I get up to the melting point for H2O, 0 degrees Celsius. And I keep adding energy, but look, that's a flat line right there. When I have a mixture of ice and water, the temperature stops changing. As long as I have a mixture of ice and water, the temperature will be 0 Celsius. Right? As defined, Celsius used that property to define his 0. And then once all the ice is melted, then I can start adding energy into the water. and get it up to 100, where I have to add a whole bunch of energy. Look how much energy I need to add per mass to get that to melt, right? Huge. And notice the scale, and that's kilojoules per kilogram. This is thousands of joules of energy to get this stuff to change, right? Multiple thousands, hundreds of thousands, tens and hundreds of thousands to get water to steam is hundreds of thousands. It's huge, right? Lots of energy, which is why it takes forever for that pot of water to come to a boil, right? Because you're getting that mixture. You're somewhere in here in this plateau at 100 degrees Celsius, or at lower pressures like we are here in northern Nevada and Carson City and stuff, maybe 95, 96, because we're up high enough that the altitude that the pressure is a little bit lower from the atmosphere typically. Anyway, that mixture is important. We want to look at how do we quantify that. Well, we do it with these things called latent heat. Latent heat is a material property, and there are going to be two of them. There's a latent heat of fusion and a latent heat of vaporization. I'll add a link to this. I don't think there's one in here, but I'll add a link to this so you can, if you're looking at the notes. Table 1.4 in the book has latent heats of fusion and vapor. Fusion is the freezing melting point. Vaporization is the condensing vaporization point, right? Condensing boiling point for substances. And they happen at particular temperatures, right? And maybe even particular combinations of temperature and pressure. We're assuming standard atmospheric pressure in table 1.4. But here's what we do. That latent heat is really an energy per change in mass. The change in mass is how much of the stuff has changed phase, right? So I'm going to put a little box around this. This is important. The change in mass of the higher phase material. So for the case of liquid water to frozen ice, to solid ice, how much of the stuff started as water is M initial in that little delta M equals final minus initial, right? M initial is how much started as water. M final is how much ended as water. Because that higher phase means sort of higher energy, higher temperature phase. How much started in the higher phase, the higher temperature phase, that's M initial. How much ended in the higher phase, that's M final. So in the case of, say, that we just looked at, we melt an ice cube. How much started as water? None of it, 0. How much ended as water? All of it. However much we started with, right? In practical terms, we want to use this Q for L delta M. Anytime we have a substance that undergoes a phase change, which we have to know, did it go to its phase change temperature? We need to look at the table and go, oh, water, ice melts at 0 or water freezes at 0 Celsius. If I'm getting to a 0 Celsius temperature, then I need to be sure I include a term for all of the H2O that includes an L delta M, right? If not all of the delta M changes, guess what temperature is the final thing? If I have a mixture of ice and water, temperature is the phase change temperature, 0 degrees Celsius in that. If I have a mixture of water and steam, the temperature is 100 degrees Celsius. This L delta M becomes an important thing for keeping track of these phase changes in latent heat, right? So the latent heat of fusion, like I said, is from solid to liquid, vaporization from liquid to gas, or vice versa. They're the same number at that thing. If energy enters, Q is positive, delta M should be positive, right? If Q is negative, delta M should be negative, Q should be negative. Keep those rules in mind for latent heat. We'll look at an example, and we'll continue more discussion of temperature and heat and thermodynamics in the next video.